live lecture, and then I iconify the thing, right? Because I forget sometimes. So you gotta, if you see me forget, let me know. If you ever see my mouse go down here and you don't see that little icon right here, the red, that means the recording isn't going. So let me know if you see that as well. Basically what I'm doing is I'm doing a screen capture and audio capture, which I'll post on YouTube. Okay, this is CS 4150. I'm Joe Zachary. Welcome to you all. Let's get started. First thing I want to do is go over some the highlights of the syllabus. Okay, so this is not an introductory course. There's some prerequisites. So what I expect that you have in the way of prerequisites is a background in basic algorithms and data structures. In other words, 2420. So that includes things like sorting algorithms, searching algorithms, lists, trees, hash tables, big O notation, that sort of thing. I recognize that some of you will be pretty rusty on that stuff, and so we'll do a little bit of reviewing at the beginning. But you need a solid background in 2420 to do well in this class. I expect that you have some programming competence. You're able to convert a high-level description of an algorithm into code, right? So I expect you're able to program. That's 2420 as well, I guess, 3500, whatever. Discrete math, 2100. We'll be using discrete math in the class to describe algorithms. So you need to be comfortable with things like exponents and logarithms, summations and products over series, proofs. We won't do a lot of proofs, we'll do some. Basic probabilities, sets, functions, relations, graphs, and trees. So that's just the language of mathematics that we'll be using. So that background is important as well. So that's why all those prerequisites show up for 4150. All right, now in terms of what you'll be doing each week, there'll be a problem set due each week. So they come out on Thursday and or Friday. I'll aim for Thursdays. And they're various kinds. Some of them are, multiple choice quizzes on Canvas. So a lot of times we'll be studying a particular algorithm. I want to see, do you understand just how it works? And so I'll give you an example and I'll say what happens next, what happens next, what happens next. And just clicking through making choices. And those are typically fairly easy quizzes, and TAs love them because they grade themselves. So there are all kinds of advantages to them. Then some of the others will be, you might have to write a few sentences to answer a question. So again, it might be on Canvas. Questions are short answer questions. And some of the assignments you'll write longer things, which I call essays, but that might be a couple paragraphs. Now, most of these quizzes and written assignments would be done on Canvas. Some of them I'll probably have you do on Gradescope, but I'll tell you when I give the assignment whether to submit to Canvas or Gradescope. And then finally, most weeks, there'll be a programming problem related to an algorithm we've studied. And that will, you'll be completing it using a website called Caddis, and I'll have more to say about that either today or on Thursday. Typically, the written problems will be due on Thursday, a week later after they come out. And the programming problem, you get an extra day. That'll be due on Fridays. Sometimes there's a written problem that's related to the programming problem. In that case, that written problem will be due on Friday as well. Anyway, weekly problem sets. I have a late policy. So right now you each have 15 late days to use. And you use a late day when you submit a problem, not a problem set, but a problem. A problem set might consist of 5 or 6 problems. So if you submit a problem a day late, then you've used one of your late days. You can use your late days until Saturday, basically. So if the thing was due on Thursday, you can use up to 2 late days and hand it in on Saturday if you want. If it was due on Friday, you just got 1 day of late day to use. And it's up to you to decide how to use the late days. A lot of you are going to get sick at some point in the semester. You might want to save up some late days for when that happens. you already have some conflict with you got to travel for work or something. So for both foreseen and unforeseen circumstances, these late days exist. Okay? I have had students use them almost all up on the first assignment because they didn't understand that it's per problem, not per problem set. So don't make that mistake. Grading is basically split half between the problem sets and the exams. So there are two exams. There's a midterm on February 27th, and the final is on April 23rd, which is the first day of finals week. So we'll have class on April 21st, and then reading day is the next day, 22nd, and then the exam is on the 23rd, so it gets over quick. And like I said, the problem sets are half your grade, and the midterm is 20%, the final 30%. So you need to do well on both. In fact, you need to get at least a 60 average on both components. The exam average, which would be weighted more toward the final, and the problem set average need to be at least 60 to get a C- or higher. So don't ignore one. Can't ignore either of those aspects. We'll make extensive use of Piazza. I used to have to explain about Piazza, but I'm sure you all know what Piazza is. But you don't need to, don't email me, don't email the TAs. Just use Piazza to communicate with us. Okay, now cheating policy. This isn't meant to be flippant. In my syllabus, I have a more detailed description of what I expect. But here's the thing. I'm not going to stand up here and tell you that you can't talk to other students about assignments. And the reason is, it's a great way to learn. Working with other people is a great way to learn. I got here to class almost 15 minutes early, and all of you were just talking to each other. You're very social people. And I'm not going to say you can't do that just because you're working on an assignment. But there are limits to the degree of cooperation that I can allow. When I say cooperate, I mean you can discuss how to approach problems. If everyone's sort of stumped on it, you can try to figure out how to solve it. But what you may not do is sort of write down a group model solution that you then all go off and type in. Anything when you actually take the quiz, or submit a written problem or whatever, you need to be doing that by yourself. So you don't sit in a group and say, oh, what's the answer to this one? You all type. What's the answer to this one? You all type. Do you see the distinction? Discuss, separate, and then actually do write your solution and submit. And you need to avoid, the ideal group is a group where you all sort of have the same level of understanding of the material. A dysfunctional group is one where you've sort of got one person who knows everything and everyone else is just sort of looking at that person to explain all the answers. It needs to really be a collaborative situation. Okay? I have spent a lot of time right before Christmas and yesterday and today so far having very uncomfortable meetings in my office with students from 1410 last semester that are going to be failing the class because they cheated. So don't do that. I don't like these meetings any more than you do. Any questions about that or anything else? I'm always happy to be interrupted and ask questions, so don't think I'll be offended. Like I mentioned, I'm going to attempt to videotape all the lectures and upload them to YouTube. There's a link on the Canvas page. Actually, right now it's a link to last year's 4150 videos, but I'll update that soon. You may come to rely on my videotaping, but I almost always mess up at some point during the semester. There's so many ways things can go wrong. So I encourage you to come to class, participate actively, and use YouTube as a backup and to review. If nothing else, if you come to class, you'll know what I look like. I was talking to David Johnson before class, and he was amused that some student that was in 1410 last semester went to see David because he's got to retake 1410. And David was amused because the student apparently thought that David was me. So the student never actually seen me. Okay, let me tell you what we'll be covering. We'll start in the first week and a half, 2 weeks, with kind of a review of material from 2420. So a review of algorithm analysis. And as we do that, we'll be talking about things like sorting algorithms you may have seen in 2420, and binary search trees, hash tables, that stuff. So really, for the first couple weeks, it will start pretty slowly. Then we'll start talking about sort of categories of algorithms. So the first category we talk about are divide and conquer algorithms. So what is a divide and conquer algorithm? Who could tell me an example of an algorithm that uses divide and conquer? Yes.
Merge sort.
Okay, merge sort, for example. So someone else tell me what makes merge sort a divide and conquer algorithm? Okay?
You take your list and you split it into segments until you get down to just 2 items and you swap them.
Okay, well, yeah. So he's saying you keep splitting the list in half and half until you get down to single item. That's more detail than I wanted. So someone else tell me, a higher level, what makes merge sort?
Instead of dealing with the list as a whole, it deals with individual elements and goes from there.
Okay. I wouldn't say individual elements, though. I would say, we'll take one more shot, yeah.
It splits up the work among different sections.
Okay. So the hallmark of a divide and conquer algorithm, like merge sort, is you have a problem, you split it typically into half. It doesn't have to be, but usually you split it into 2 pieces. You solve the pieces individually, often recursively, but you solve them, and then you combine those 2 solutions into an overall solution. So with merge sort, you split the array into 2 halves, you sort the 2 halves using merge sort, and then you use the merge algorithm to merge them together. So that's the divide and conquer algorithm. Involves the splitting, the solving, the recombining. And you've seen examples of, a number of examples of divide and conquer algorithms. We'll study divide and conquer in more detail and look at divide and conquer algorithms that you've probably never seen before. Okay, then we'll get into, we'll spend a fair amount of time talking about graph algorithms, and you talked some about graph algorithms in 2420. We'll talk about it more. The discussion will be broken into 2 pieces. One is graph decomposition, which is taking a graph, sort of analyzing the graph and extracting information from it. That's we centered around depth-first search. And then there's the problem of graph traversal, which is taking a graph and searching for the shortest path or a path or whatever. And that's going to be centered around breadth-first search. Okay? Now we have a book that we'll be following. You have a copy, don't you? Hold that up. Okay? That's what the book looks like. It's available online, from Amazon. It's available in the bookstore, I think. But there's also a PDF, a free PDF on the author's website. So a lot of students just use the PDF. One thing I warn you about the PDF is I've never found any inconsistency between it and the printed book, except occasionally the figures have different numbers, and the problems at the end of the section, at the end of each chapter, are numbered differently. So I've stopped using, if I assign something from the book, I won't use the problem number, and so on. So it seems to work out well to use that PDF if that's what you wish. But the book is actually fairly inexpensive, at least as textbooks go. Anyway, I'm mentioning that because that review of algorithm analysis, there's a very short chapter 0 in the book. So if anything, it corresponds to that first step. Divide and conquer is chapter 2, and then graph decomposition is 3, and then graph traversal is 4. Then we're going back to chapter 1. So you may wonder why I come back to chapter 1 in the middle of the semester. It's because the material in there is unlike any that you've probably seen in 2420, and it's proven over time to be a hard way to start the course. So I just look back and look at it. And what we'll look at there are number theory algorithms with the idea of understanding how public key encryption works. So basically algorithms that work on gigantic integers. That's about halfway through the course. In the second half of the course, we start looking at more, instead of at individual algorithms, we look at more algorithm design techniques. And so the techniques to be looking at are greedy algorithms, dynamic programming, linear programming. Well, I guess those are the three main ones. Greedy algorithms, dynamic programming, and linear programming, which are classes of algorithms. Then we'll finish up by looking at the theory of NP completeness, which is basically a, no, I won't try to summarize it right now, but we'll talk about the NP completeness, and really the two chapters that discuss NP completeness, a more theoretical topic. Okay, so that's what we're covering. Any questions about that? Any worries or? Okay, now, I know most of you in here because the class is required. But if it weren't required, I know that people would be taking it anyway. I'd be interested in hearing from you right now. What do you hope to get out of the class, other than a passing grade? Yeah.
I'm certain a lot of the algorithms are applicable in various aspects of game design and
Okay.
programming, like AI and such.
Okay. So he mentioned game design, algorithms for game design. Yeah.
There have been some interviews that I've had that I feel like I would have probably done better on had I been in this class instead of like, except for like, I just have my knowledge of like 24 at this point, so I feel like this class is going to extend that knowledge.
Okay. So that's a good point. I've had a number of students come back and say, I had a programming interview last week, and we discussed the very problem that was on the assignment. That was on the interview. So yes, this class can really help with those types of interviews. Yeah.
It seems like a lot of research positions that I've looked at, oftentimes they point to algorithms as like a good foundational class.
Okay.
To
So.
get an understanding of what the work they're doing is.
Okay, so he's mentioning research positions often suggest taking this class. This really, algorithms is the heart of computer science. And people have been studying algorithms long before there were computers. One algorithm we'll look at is Euclid's greatest common divisor algorithm. It's 2,400 years old. So it's an ancient field. Yeah.
Aren't you able to develop more efficient solutions to problems faster instead of just not knowing where to look and turn?
Okay, so develop more efficient solutions faster. Anything else? Yeah.
Like anything above basic programming, it's really helpful to not have like just a black box look at how certain like things work and like for architect situations.
Okay. Okay, so people have different goals, and that hopefully satisfy most of them. All right, we're going to look at an example here. Try to set the stage for the semester. So here's what a cynic might say about 4150. Why it's a useless course, let's say. So they might say, one algorithm is as good as the next one. If I know one way of doing something, then that's enough. There's no need to study algorithms because I can find one on the web whenever I need one. I'll just go to Stack Overflow and say, what algorithm should I use for this problem? There's sort of a cynic might say that this is just ivory tower academic stuff. Just use the libraries in Python or whatever, and everything's going to work out just fine. They might object to my use of pseudocode or the book's use of pseudocode. In fact, I typically won't write much code in Java or C# or Python or whatever. I'll just write in pseudocode. Some students bristle at that. They want an implementation in a real language. So I'm just throwing those up there because we're going to look at an example. We'll come back and think about these objections later. Okay, this is something called Jumble. And the idea, this game shows up in the Tribune every day, and this version is taken from offline. What you do is, over here on the left, is those are anagrams of words, so you unscramble them. So help me out here. What's the first word? Shove, and then going, ticket, avenue. I never did, it helps to have 160 people taking this. Then the letters that you write the unscrambled words in those boxes below, and then in the circled letters, that's another anagram. That's the answer to this question over here. So we see the passenger in the car saying, "Wow, traffic is really bad for a Monday," and then the driver obviously has a cold and says, "I'm out of tissues," and it says the driver with a bad cold wasn't happy with all the blank. Congestion. So sometimes you can get it just from the clue. Other times you have to actually work the anagram. All right, so that's the basis of the example I'm about to do. So it occurred to me, when I was doing jumbles, these guys have been doing this for years and years and years. And on Monday through Saturday, you get a puzzle with, I guess in the paper it may be three five-letter anagrams and 1 6-letter anagrams. And on Sundays, there's maybe more anagrams and they're longer, maybe more 6-letter anagrams. So I started wondering how many English words are there that'll work for this game? Say, how many 5-letter words are there that you could use in a jumble? Now, what property would a 5-letter word have to use it in this jumble game? Yeah.
Maybe an anagram to another word?
Right, it better not anagram to a different word. Okay? So I figure they must have a list of all the words that work. They must have developed a list at some point of all the 5-letter words that don't anagram to any other word, because you need to be able to uniquely unscramble the words for this to work. And so here's the, and I was wondering where the list came from. So let's devise an algorithm to create such a list. The input's just going to be a list of words. We'll say of length k. The output is going to be a set containing every word from that list that is not the anagram of any other word of the list. So for example, if you took all the 5-letter words in English, steak, S-T-E-A-K, would not be in the output because it has the same 5 letters as skate and steak and takes and teaks and maybe others. So you'd never see that in the jumble puzzle. On the other hand, shove turns out would be in the output because there are no other English words that have those 5 letters, those exact 5 letters in some word. So that's the problem we want to study. I don't want to go that far right yet. What I want to do right now is to have a little classroom exercise. I want to suspend operations for 5 minutes or so. I want you to design an algorithm for it. I have like 4 or 5 algorithms on slides I'm going to show you later. But I'd like you to think about the problem first. So talk to the people around you and figure out if you had to write, you're in a job interview, you have to come up with an efficient algorithm to produce this list of words from given a dictionary. How would you do it? Okay? So you get going and I'll cool my hands. That's enough? All right, so in the past what I've done is I've asked people to describe their algorithms, but what I find is that they're not described in the same order I want them to be described. I have a series of algorithms I want to talk about, different versions. And so I'll show you mine, and you can see if you thought of one that was different from anything I thought of. The main reason I do this is it sort of gets you invested in the problem. You understand it a little better. Makes it so that what I'm about to do makes more sense to you. All right, here's the first version, sort of the simplest version I could think of. Dictionary is just going to be an array list of words. The words that we're given, you stick them in an array or an array list. And then we're going to have a set that I'll call solutions, and that starts out empty. Then we're going to look at every word in the dictionary. So we loop through every word in that list. We have this variable count, which we set to 0. Then we consider every permutation of the word. Now, how many permutations will there be if we've got like 5-letter words? 120. 5 factorial. Okay? So that loop would run 120 times. And we permute we take a permutation of the word, then we look to see if it's in the dictionary. If it is, we increment count. When that loop is over, if count is 1, what does that mean? If count is 1, it was in only one permutation was found in the dictionary, presumably the original version of the word. That would be one of the permutations. And so we add it to our solution set. On the other hand, if the count's bigger than 1, then there were multiple permutations that were words, and so we don't add it to the solution set. And then when we're done, we just return our solution set. Okay, that makes sense? Pretty simple to describe, pretty simple to code. What do you make of it? Is that a good algorithm, a bad algorithm? Would it a long time?
I mean, I'm assuming it's bad because it's the first one you showed.
Okay, true. It's jumble 0. That's not a good sign. But what does it mean to be a bad algorithm? It works, doesn't it? Yeah.
It has bad complexity for the problem. For example, this one should have complexity of like n squared.
Okay, so it says the complexity is bad. It says it's an n squared algorithm. I want to point out something though. There are actually two variables here. We'll let n be the number of words in the list to start with. And you're right, it's n squared in that case. But also, it's also sensitive to the number of letters in the words. So, and we'll call that k. So
N squared times k.
So there's a k factorial lurking in here somewhere too, because you have to look at, for every word, you got to look at k factorial permutations. For right now, let's let k. We'll assume k is constant, something small like 5, and not worry about it too much. Okay, so there's a sense that maybe that it's an n squared algorithm, but so what? How long would it take to run? How fast does it need to be? If you are the jumble people, you need to run this program once in your life. You give it a dictionary of 5-letter words, I guess twice. You give it a dictionary of 5-letter words, you run it once. You get your list of 5-letter words you can use, then you do the same for 6-letter words, and you never run it again. So if it takes 5 minutes to run, it doesn't really matter, does it? No, not in that situation. But let's suppose we live in a world where we think of other applications for this beyond the jumble game. Maybe we're working in genetics and we're interested in permutations of I don't know what the term is in biology for the Gattaca, GTCA, those things in your DNA. But anyway, imagine that your dictionary can be huge, massive, the genomes of everything on Earth, and the sequences can be really long, so lots of permutations. In that case, efficiency does become a concern. So what are some easy things to pick at here? What are some obvious things you could do to speed it up? Yeah?
You can just, whenever you count, if it ever goes over 1, you can just immediately break out of that.
Okay, so one observation is that for each loop, if count goes over 1, you can just quit. Okay, that's another thing, yeah?
Sort the words alphabetically so you don't have every permutation.
Okay, we'll see that sort of thing toward the end. Yeah? I'll explain that more toward the end too. What else could we do? Yeah.
You could remove repeats from the dictionary. So like when you're checking steak, if you find skate, remove them. That would probably.
So sort of shrink the dictionary as you.
Yeah, like if you check steak, you don't need to check skate again, or they permute to each other.
Yeah, I think it's sort of related to stopping the loop early once you find the match. But yeah.
Maybe only check for a subset of the dictionary that has the same length as the string that you're checking.
Yeah, I'm gonna assume the dictionary is all words of the same length. What about using ideas from 2420? Yeah.
Make the solution set a hash map.
Well, the solution set doesn't need to be a map. The solution set, in fact, isn't a set right now. But focus on the dictionary. Yeah.
Have a different type of container, so like a hash map, so you can look it up quickly.
Okay. So, think about this step where we, if P is in dictionary. How do we do that operation? How do we check whether a string is in the dictionary if it's a list?
We have to build a list.
Just got to do a linear search through it. It'd be a lot better if it was like a hash set, and you have a really fast way of looking at that. Okay? So those are all ideas for improving things. So this is the first change I'm going to make. Jumble 1. I'm going to change the dictionary so instead of being a list of words, it's a balanced binary search tree of words. So in Java, that would be a tree set. Right? So that's a speed up that we talked about. So I guess I already told you, but you can tell me again. How does this speed up the program?
It makes the if P is in dictionary step.
Right. It speeds up the if P is in dictionary step. So rather than that requiring linear time, we're having to look at the entire dictionary potentially. You can look it up in constant time. So it speeds up that if P is in dictionary. And notice that if P is in dictionary is inside a loop that's running k factorial times. So it's a big payoff to make that faster. So that's Jumble 1. Jumble 2, I'm going to make another minor change to the program, speed it up a little bit more. What's another thing you could use besides a balanced binary search tree to speed up the thing? Yeah?
Maybe the way that we iterate through it could be faster?
Well, yeah, there are things about like that, but I'm talking about what could we replace that yellow text with to make it even faster.
Hash set?
Yeah, hash set. Hash table. So we'll just use a hash table containing the words, and a hash table is going to be typically faster. It's not massively faster than a balanced BST, but it is faster. So we could do that. We would see a speed up. Okay. Jumble 3. So we're going to keep the hash set, but I'm just going to put that suggestion in. So once the count gets greater than 1, we'll break out of that inner for each loop. So we'll once it gets to 2, it doesn't matter if it's 3 or 4 or 5. We know it's bigger than 1, so we can stop, and the word won't qualify. So that's a way to speed it up. And so the first program is just sort of a very straightforward way of doing it. The next two, Jumble 1 and 2, you're applying knowledge that you have about properties of data structures in your programming language. Knowing, that's a reason you take 2420 is to know that it's a lot better to search for something in a set, a hash set or a binary search tree set, than it is to search through it in a list. That can make a dramatic improvement in efficiency. Now we're more into sort of algorithm tweaks. In a sense, this is kind of a different algorithm. We're not using a different data structure, but that code could make a big difference, or maybe not. We'll see. Here's Jumble 4. Now this is I want to see where I'm headed. Yeah. Okay. This is going to be different. This is different from the previous 3. This is a completely different approach to doing it. So what we're going to do is have our dictionary again. It'll be an array list containing words. Then we're going to have a set that starts out empty called solutions, as before. And then we're going to have one called rejected. So the idea is that when we're done, we'll have a set containing all the words that are our solution that we've accepted. and then rejected will contain all the rest of the words. So the job of the algorithm is to put the words into one of those two sets. And so what we do is, for each word in the dictionary, if we look at all its permutations, and if one of them is in solutions, we remove it from solutions and add it to rejected. Right? I'll come back to that in a second. Otherwise, if none of the words permutations are in rejected, we add the word to solutions. So let me just, I think it's going to be easier to show you what's going on just by going through an example. So what we do is we look at T, and we ask the question, let's see what question we're asking here. Are any of the permutations of this word in solutions?
No.
Okay? Solution is empty, so it's not there. And so we put it in solution. So the way to think about it is, we looked at the first word so far, and at any given point, solution will contain all the words that are acceptable given the words that we've looked at in the dictionary so far. Now, looking ahead, eventually T will come out of solution and be stuck into rejected. What will cause that? We get to E into 8. They're going to anagram, they're anagrams of T, and so T will be kicked off into rejected. Okay, then tip. Okay?
It's not in the solution set.
It's not in solution, so we put it there. Well, let's make sure. What are we checking again? First, we check if it's in solutions, we stick it to rejected. Otherwise, if it's not in rejected, we add it to solutions. Okay, so we do that, we do that. What do we do with rat? It hasn't been, it has not, none of its anagrams have been rejected, and it's not in solution already, so we stick it there. What happens with eat?
One of its anagrams is in solution.
Yeah, one of its anagrams is in the solution already. Okay? So that means both eat and T
Gonna end up rejected.
are bad. And what I said earlier was a little lie. We don't put both eat and T into rejected. We just need one of the anagrams in there. So at the end, solution will contain all the anagrams, all the unique anagrams, and rejected will contain all the non-unique anagrams, but only one example of each. What about pit?
It's in there. It's in solution.
Yeah, pit and tip are the same, and so we got to kick it out of solution into rejected. And then we see 8, and it's already in rejected, so we're done. Okay? So that makes sense? So bottom line is, one pass through the dictionary, we're having to check to see whether things are in sets. Let's see if I've got the, okay, here's the algorithm again. Is this more efficient, you think, than the other way?
Yes.
See, it's more obscure, certainly. Well, what have we improved?
Instead of n squared, it's n now. It's only going to the array, the dictionary once.
Well, it goes to the dictionary once. It's still got to generate permutations. And it's still got to check to see whether permutations are in sets. Yeah?
It doesn't have to generate nonsensical permutations.
Well, what do you mean it doesn't have to generate nonsensical?
So, in other words, in the original solution, if you had, say, steak, you wouldn't have to check the non-void permutations, such as T, A, K.
Well, okay, let's come back here. T, tip, rat. Okay, we get to eat. What do we have to? We have to generate the. We have to figure out: does T show up in rejected, and does an anagram of T show up in rejected, and does an anagram of T show up in solution? So we've got to generate somehow. We've either got to anagram the words in the sets, or we've got to anagram the word itself. So it's not. I think this actually turns out to be faster than the other algorithm, but it's not. It's not immediately obvious to me that it is. Just looking at it here. I mean, it's harder to understand, and it's more. It's a little more complicated. And the only reason I'm doing this is as a stepping stone to the final version algorithm, which is clearly better. But it's important that you understand this one first. So let's just look at it again. If one of the words, if we got a word we're looking at, if one of its permutations is already in solutions, then that means that the word we're looking at and that word in solutions are the same, anagram to the same thing, have the same letters, and neither of them can be in the final solution. So we dump one and put the other in the rejected set. Otherwise, if it's not already in solutions, and it's not in rejected either, then we add the word to solutions. Question? Yeah?
No, I think I understand why this algorithm is better.
Mm-hmm.
It's because you have to compare words to see if it's an anagram less. Like, in the previous anagram, you would have had to compare eat to every other word, whereas when it's the first one we're adding, you don't have to compare eat to anything.
Well, yeah, the sets start out empty.
But in the previous algorithm, we would have had to compare eat to every other word in the dictionary. So we're making a
Yes.
lot less
Okay.
comparisons.
Right. So okay, maybe that's what you were getting at too. So when we start out here, the sets are empty and they grow. And so early on in the algorithm, the job of deciding whether the permutation is in the set is easier because the sets are smaller, as opposed to having to look through the entire dictionary every time. Okay, that's a good point. But we need to do something about this permutation business. We need to avoid generating permutations. That's going to kill us if K gets long. And someone's already suggested the answer. But yeah.
So what you could do is you could assign all the letters A through Z to the n prime number, and then just index it by the multiple.
Okay. Okay, so what he's suggesting is to come up with a way of mapping a word to a number such that every permutation of that word maps to the same number. And so he's using a trick, basically a Gödel numbering. But rather than go in that direction, there's something that's simpler to explain anyway. Yeah.
You can sort the words.
Just sort the words, because you take those, steak and teaks and skate and so on. If you sort them, they'll all sort to the same thing. So here's the deal. Jumble 5. We take a word from the dictionary, we sort it, and then we don't have to worry about permutations anymore. Then we just say, if that sorted word is in solutions, remove from solutions, add to rejected. Else, if that sorted word is not in rejected, you add it to solutions. Okay? So no permutations needed anymore because we're just, we sort the words first. We sort the letters of the word. Let's see how that works. So there's T. So we sort it to get AET, and it wasn't in, is neither in rejected or solution, so it goes into solution. What's going to happen with tip? We're going to sort it into IPT. We don't find it in either set, so it goes into solution. Rat, ART, it goes in there. Okay, now we get to eat. What's eat going to sort to? AET, and it's, we don't have to do any permutations at that point. It's just sitting in solution. So we go to rejected. We look at pit, that goes to IPT, that's in solution, so it gets kicked out. And then we see 8, it's in rejected. AET is already in rejected, so we ignore it as well. Okay? So that seems like a big improvement because we don't have to do any permuting at all. We just do a sort. But there is an objection to it, and I'll let you make it.
No, we have to unsort the word at the end of it.
Right. So we were supposed to come up with a list of words we could use. Instead, what we've got is a list of anagrams of words we could use. Yeah. And we could solve that problem if we cared to, but it would complicate the algorithm and sort of obscure my main point. So besides, to the guys doing Jumble, this is as good as it's good enough.
I was just going to say that. Just throw the anagrams on the
Right, they're already anagrammed. Yeah.
I was theorizing with Skylar here that if we wanted to, we could make a small struct with the sorted word version and
Yeah.
the proper word.
Yeah. So he's saying you could make a struct, an object of some kind that held both the original word and the anagram. And it wouldn't increase the complexity of the algorithm. It just the runtime complexity. Just make it harder to talk about. Yeah.
One of the problems that I see is we did spend a whole half of the semester talking about how hard sorting things is.
Well,
But it's easier than the
it's far
permutation,
easier.
but
Sorting 5-letter words is pretty easy.
That's fair. They're short.
And even sorting 100-letter gene sequences is easy too, compared to generating 100 factorial permutations, which is impossible, practically. Okay, so let's go back to these possible objections to CS4150. One algorithm is as good as the next one. I mean, all those algorithms we looked at work, but depending on how big the input is and how long the words are, some of those algorithms, most of them, would be unworkable. The ones that actually require generating permutations just would not work in any conceivable amount of reasonable time if the words were long enough. So one algorithm is not as good as the next one, even if they all work. There's no need to study algorithms. I can find one on the web whenever I need one. I don't know if you could find this algorithm on the web. I mean, I've been teaching it for so long. Actually, you can. The slides are on the web after all. But algorithm, it's not unusual to have to come up with a new algorithm to do something. You've got some part of your program that's not fast enough, and you've got to have the chops to be able to figure out why it's slow and what to do about it. Now, sometimes it might be just to use a different data structure from the library, but other times it might take this little aha, if I sort the words, it can make it faster. And it just takes practice and experience to be able to come up with ideas like that and try them out. This is all ivory tower stuff. I use the libraries in my favorite language and everything works out just fine. Well, we did use the language libraries for this. We didn't try to implement sets and hash sets and tree sets. We assumed that they come with the language, but that wasn't good enough. We can use sorting algorithms from the language as well. We've got to figure out how to put them together. And then with the pseudocode, yeah, I could have written the code in Java or Python, but my goal is not to give you code that you can run necessarily. It takes more. Well, Python wouldn't take more space, but Java certainly would. I'm just trying to make it clear enough to get the idea across, and I trust that you can take that idea and run with it. Here's another possible objection. Real programmers don't do complexity analysis. I can run the implementation and see how long it takes. So we're going to chew on that one for a bit. We'll come back to that, the possible objection. So I want to show you the results of timing. I did the timing experiment. My dictionary had almost 9,000 5-letter words, and I'm going to show you the average running time in milliseconds rounded to 2 digits. So how long, this is just wild guessing really, but how long do you think Jumble 0 would take?
Just over 9,000 squared.
Well, in what units? You said 9,000 squared. Okay, just a reminder, that's what it looks like. It took 40 seconds. Okay, 40,000 milliseconds. So, as I was saying before, if you only had to run the program once, 40 seconds isn't too bad. But there are lots of programs out there that if it took 40 seconds to run, you'd be severely annoyed. So 40,000 doesn't sound too good. Now, Jumble 1, that's where we stuck in the balanced binary search tree. That's all we did was change it from a linear search to check each permutation in the set to a binary search tree search. So if the other one was 40,000, what do you think that simple change will do to it? 30,000? Less than a second. So about half a second. So that's it makes such a dramatic difference because that check, remember, that is if P is in dictionary check, is doubly nested, right? It's inside the for each you're looping over the words in the dictionary, you're looping over the permutations, you're doing that test. So getting that test fast makes a huge difference. 600. Now, the next version, we replaced the VST with a hash table. Hash table is a little bit faster than VST. So what do you think? It goes to 140. Okay? That would be, and that's sort of because, we got 9,000 words. If we had 1,000,000 words, it could be a more dramatic difference. Okay? Jumble 3. That's all we did there was we stuck that if count greater than 1 break. Okay? What do you think?
70, 100.
70, 100? Okay? Make hardly any difference at all. I would have thought it would make a bigger difference myself. Okay? Jumble 4, we did that intermediate solution where we were still doing permutations, but we were using the solutions in rejected set. And as we finally figured out, the advantage is that the test that we're doing is, instead of testing whether things are in the dictionary is always really long, we're checking whether in those set solutions in rejected, which start out empty. And so a lot of the early tests are going to be a lot faster. So I'll go back here. That was 130. What do you think for Jumble 4?
100.
100. Yes. Of course, the slides are online. You're not looking at them.
Yeah, I'm not looking at it.
Okay, and then Jumble 5, which you know what that is. So 100, remember, that's a tenth of a second. 100 milliseconds. There's Jumble 5. 2.9. So that makes a huge difference. So back to this question. Real programmers don't do complexity analysis. I can run the implementation and see how long it takes. Yes, you can. But why should you still, having the ability to look at code and sort of say, this way would be faster than that way. Why is that still a good skill, even though you can implement the things and time them?
Because then
Yeah.
Scalability. Like if you were, the dictionary you're using was like 100 words, you'd be happy with the first algorithm because it wouldn't have taken too long.
Okay.
But if you were using the same program in an instance where the dictionary was larger, you take a bigger hit without,
Okay, right. So yeah, when you do a timing, you're looking at a particular size of the problem, and that's not necessarily going to tell you what happens in the long run. Whereas algorithm analysis would get you the answer. Yeah.
You might have to look through pre-existing code to identify where it can be improved instead of just writing 5 different versions of the program.
True. You've got to have some idea of why something is slow before you can make it faster. So you have to be able to look at the program and figure that out. Yeah.
Sometimes even though you can unit test your own algorithm when you implement it in a large scale project, it can have impact in ways you didn't predict with just a small test.
Okay. So yeah.
One test.
Testing's difficult to get a full picture with one test is difficult. Yeah.
So if it was something else that needs to be ran all the time, like maybe you're trying to build something that people at your job are going to have to use all the time, if it takes a minute, then that's a minute all your workers have to wait every time they want to run the program.
Okay.
Whereas if it's like 5 seconds, then that makes them all more efficient.
Yeah. Take one more. Yeah.
Just giving yourself extra work if you could write it right the first time.
Right. That's what I was hoping to hear. It's a lot of work. Implement. I had to do this work. I implemented 6 versions of Jumble and did the timing and all that. If you can quickly look at an algorithm and say, this thing is using permutations, and that is not going to scale at all. That's the thing. K factorial just grows too fast. It's worse than exponential. So the ability to quickly reject a proposed solution without having to code it up and laboriously test it is valuable. It saves a tremendous amount of time. You can reject things without having to code them up first. So I observed, Jumble 0's way slow, and the others are all acceptably fast. They run in less than a second. And so if you're just the Jumble guys, that's fast enough. So someone might say, well, Jumble 5 is only of academic interest. The others take less than a second. What's the answer to that? Yeah?
I mean, maybe in this particular situation that's true, but oftentimes you'll have a program that runs, that is supposed to run multiple times a second. If it's taking half a second every time, that's not going to be able to keep up.
Okay. So, if all I'll just repeat the thing I said earlier. If all you're interested in is this list of 9,000 words, it really doesn't matter. But if the problem in general can scale in either dimension, in number of words or length of words, then it's not of academic interest. It's the only solution that works if SK grows. And then someone might say, Jumble 5 is too hard to understand. I'll stick with Jumble 3. Well, that doesn't look good. That's just stubbornness. All right. So another thing I like to do during the class is take a break. So I'm going to take a few-minute break, and just what you need to see me do is bring this up. After the break, and basically recording 30 minutes of Block U with no audio. So make sure that I re-enable live lecture. Okay. Now, you have, in 2420, you learned how to do algorithm analysis, and you learned about big O notation. I'm not going to use big O today. I want to talk about a different thing. I want to try to understand the doubling behavior of these algorithms. So what will happen to the running time of these algorithms when the number of words doubles? All right, so let's start with jumble 0. There's the algorithm. Suppose that our dictionary was of length n and it became length 2n. How would that affect the running time of the algorithm? Double the length of the input, what will happen to the running time? Yeah?
It'll quadruple.
Okay, he says it'll quadruple. Anyone have a different answer? Okay, someone else tell me, why would it quadruple? Yeah?
As n squared plus the k pointers, but
Yeah, but one answer is an n squared algorithm, that's its doubling behavior. An n squared algorithm, if you double the input size, it quadruples the running time. But if you've never heard of big O notation, what would you say? Yeah.
So the for each word in the dictionary happens twice as often, and the if piece in the dictionary happens twice as much.
Yeah. The outer loop takes twice as long to run, and the inner loop takes twice as long to run. Okay? So before you were doing, how many times did that if p is in dictionary run? If the outer loop runs n times, the inner loop runs n times. No, I'll take that back. Forget about the inner loop. The inner loop is permutations. We're assuming permutations are small and fixed length. So the outer loop runs n times. There's a hidden loop. The p is in dictionary. That's a linear search. So that's sort of a loop that we're not seeing that takes n steps as well. If you double the length, so the code in the inner loop is running n squared times, because I'm just waving my hands right now. I gotta think a better way to explain it. Let me turn this on. All right, if we just run this loop, if we run this loop twice as much and nothing else changes, the program's going to take twice as long to run. Okay? The problem is, yeah, this loop now runs twice as much, but also this test takes twice as long because the list is twice as long now that we have to search through. So you multiply those together, it comes up, 2 times 2 is 4. So yeah, it takes 4 times longer. You double the length of the running time of the input size, it quadruples the running time. What about this one here? Okay, so yes, the outer loop now doubles, so it's running. It takes twice as long. This test now is no longer having to search the entire list, but the cost of this test does depend on the length of the dictionary. Okay, so one answer is it's going to do worse than double. It's going to double because the dictionary is twice as long, and then there's going to be some penalty because now the dictionary is longer. This test here will take a little bit longer because it takes longer to search in a binary search tree for something if the tree is bigger. So it doubles plus a bit. Okay? What about this one here that uses a hash table? Yeah, it doubles plus a bit. I guess I could said it doubles. If you assume that the lookup time in a hash table is constant, then it's just going to flat out double. Okay, what about here? Let's assume we're talking about the worst case scenario. Well, where'd the less a bit come from? Well, what would the worst case be, though? If all the words were unique anagrams, you would never make that break. So in the worst case, that break doesn't matter. So you get the same answer. It just doubles in the worst case. This one here is a little bit harder to get your head around, but turns out it also doubles. What about this one here? Yeah. Also, the stuff in the loop goes fast. That's all sort of constant time stuff, assuming that words are a fixed length. And so it's just going to take twice as long. So if you look at that, if you're trying to predict which algorithm is going to be faster in the long run, it doesn't look too bad for Jumble's 1 through 5. They all sort of have the same apparent complexity. You double the length, you double the running time. And sure, Jumble 5 is faster, but and as N gets bigger, though, they're going to grow up the same rate. On the other hand, Jumble 0 is clearly going to be a disaster. Its running time will grow faster. So that's part of it, but we've already talked about that, so I will skip it. Now, let's consider what happens when N stays the same, but K grows. The length of the words grow. Okay? So now we'll have the same 9,000 words, but we're going to let K grow. So what happens now? What's going to be affected in the program by the length of the word?
Multiply by 1 plus the old length?
Yeah, the number of permutations. So if K, let's say K goes up by 1. K increases by 1. So before it increases, that inner loop, that for each distinct permutation, how many times does that inner loop run?
K factorial.
K factorial times. How many times will it run when there's K plus 1 letters in a word?
K plus 1.
K plus 1 factorial. What factor of increase is that? If you divide K plus 1 factorial by K factorial, what do you get?
K plus 1.
K plus 1. So the running time goes up by at least a factor of K plus 1. So if you go from 5-letter words to 6-letter words, and you have the same number of words, the program's going to take how much longer?
6 times.
6 times. And then you go to 7-letter words, it's going to take 7 times. That's bad news. Okay? And that's not counting the problem that other things take longer when the word goes up, when the word gets longer. What would take more time? Which operations in here could take more time because the words are longer? Yeah. Yeah, when you're doing the comparisons of words, the words are longer, they could potentially take longer to compare just because there are more letters to look at. That's why I say at least K plus 1 times longer. What's going to happen here? Same analysis. We're just looking at that inner loop. When you increase K by 1, you're going to increase that inner loop or run K plus 1 times more. So it takes at least K plus 1 times longer. Jumble 2, same deal. K plus 1 times longer. Jumble 3, Jumble 4, all the same. And I just want to emphasize how terrible that is. So your running time, which was say half a second, with 5-letter words, 6-letter words is now 6 times longer. So now you're at 3 seconds. You may go to 7-letter words, you're 7 times longer. That's 21 seconds. Before long, you're hours and days and years and centuries and millennia. Bad. What about here, though? There are no permutations. So what happens to slow this program down as K increases? Yeah. Sorting's more expensive. Slightly. It's not like, it's just very slightly more expensive. You go from K log K to K plus 1 log K plus 1. It's almost negligible. And actually the lookups can be slightly more expensive just because the keys are longer. So it goes up slightly, but it doesn't make much difference. And so when you think about those timing results where, like I'll go back to them. I have to go back a long way, sorry about that. Right there, where it looked like Jumble 1 through Jumble 5 were all pretty good. When you start letting K grow, Jumble 5 is going to stay down there pretty close to 2.9 as K starts growing. And those other ones are just going to get ridiculously slow really fast. So there's something to this algorithm analysis stuff. What I want to say is I assign these caddis problems, and we study some algorithm, find a fast way to do something. In fact, your first caddis problem will be this algorithm right here. And for some reason, there's some students that stubbornly say, yeah, I'll do it my way. And I'm just always astonished that they implement they're implemented their way, and it's not fast enough, and it doesn't pass the test cases in Caddis because you've got a limited amount of time in Caddis. And they wonder why. Well, you didn't do it very efficiently. All right, so to wrap up, I want to show you what Caddis looks like because you'll be spending some time in Caddis. So this is sort of this is an example problem in Caddis. Caddis as a site has all kinds of programming problems. This one here, usually there's a little story, and I'll just tell you quickly. Alice travels for work. She visits cities, and people ask her, how many different cities have you visited for work on a trip? And you're supposed to calculate that. And so just to make a long story short, Caddis will typically have a description of stuff, and this is sample input. So what this is saying, if I were to let you read the words up here, it would say there are 2 test cases. One test case consists of 7 cities. So think of this as Alice took a trip of length 7, and these are the cities that she visited. And then her second trip, she visited 3 cities and was in Edmonton all the time. And your program is supposed to put as output 4, which is the number of unique cities she visited on that trip right there, because notice Saskatoon is on there twice and so on. And then for the second test case, you output 1, because there's only 1 unique city there. So that's a pretty simple problem. Your job is just, you do not check for errors. You do not check, you assume the input is formatted correctly. You just produce the output required. People fail these tests because they take too long. They also fail them because they produce debugging output. Like they stick debugging output in their code, and then they don't take it out. And then they run it, and Caddis is expecting to see 4 and 1. And it doesn't see 4 and 1, it sees 4 and then some debugging output and then 1, and that's no good either. So you've got to stick pretty strictly to what it says. The output has to be exactly like it's supposed to be. And you can trust the input to be exactly what it's supposed to be. So let's try to solve this problem if we can in 5 minutes. So I'll do it in Java. I got started here. So what's a way to approach this problem? How should we do it efficiently? Yeah.
Just like the way we did Jumble, we'll probably sort every single word.
Well, you talked about sorting the cities, but no, we don't need to sort them. Yeah. Right. All you have to do is throw these things into a set and output the set's length. And do that once for each test case. Okay? So let's try that out. So first thing we have to do is get the number of tests. I should have I solved it for a class. I used to type much better than I do now. All right, so I just want to point out a few things. So just writing a program, you read your input from standard in. Okay? In Java, that means you're reading from system.in, you're writing to system.out. Okay? You do not prompt for input. You just assume the input will appear and you read it. And then you do not say, here comes my output. You just output what you're supposed to output. If you're programming in C++, you'll use cin and cout, and so on. So I create a scanner to read from system.in. First thing I do is I read the first line, and that's the number of tests. And then I wrote a loop there that calls solve t times. So solve solves each test case. The sample input had 2 test cases. Then we call solve, and solve takes the same scanner. It reads the number of cities. It creates an empty set. It reads every city, which is a different line, and throws it into the set. And then it outputs its length. So that's the solution. Okay? Now, once you've done that, you ought to test the program in your own programming environment. So let's test it. What I'll do is I'll run the program, and it wants some input. The thing to do is to go here to the problem statement, copy the sample input. Got to copy all of it. Come back to your programming environment and just paste it there. And be sure to stick a new line at the end. And it'll come out in some wacky order, but the thing to realize is the green is what I input, and what it output is the black in the case of Eclipse here. So it output 4 and 1. So you can see that that works. You can write your own test cases. I really recommend you do that. Then when you're ready to submit it to Caddis, all you do is you go in here to Caddis. You come up here to Submit. You get to pick your language. Those are the ones you can choose from. Is COBOL on there?
Yep.
Wow. Okay. I look forward to seeing COBOL solutions. Oops, wrong thing. You take your program, come down here, and drop it there. Main class is caddis.everywhere, Java. I submit. And it takes a while, and it runs it against its test cases. In this case, there are only 2 test cases, the one that it gave you, the public one, and one that it's not showing you. You'll find out if you fail a test case, you'll see a red X. If it takes too long, it'll tell you it took too long. If it throws an unhandled exception, it'll just say there's a runtime error. You get very little information out. It's a terrible way to debug. If you're going to debug, you need to write your own test cases. Okay? I'll end there, and I'll take your question up here.